So in this part, we want to see how to apply the crystal field theory to understand the properties of this metal complex and including the magnetic properties. So crystal field splitting, the delta energy difference between T2G and EG is depending upon what kind of ligand the complex contains. The size of energy gap is depending upon the type of the ligands. So here it shows different types of ligands: cyanide, nitrate, diethylamine, ethyl and amine and aqua water, hydroxide, and all the halide anions. And they are different in their energy splitting. Here, left hand side, the red one's energy splitting is now large, and the black one's energy splitting is relatively small. The difference here is now amine and water. And so up to amine, so cyanide and NO2 negative, and diethylamine, ethylene diamine, and NH3, we call this one strong field ligands. And from water, hydroxide, fluoride, chloride, bromide, iodide, we call this one weak field ligands. Let's see the meaning of this one in next slide. So size of the energy gap is now depending upon the type of the ligands. Let's see the example. Iron 2 plus. Iron 2 plus has now 6 electrons in 3D subshell. So 1, 2, 3, 4, 5 of spin. The sixth one is now paired with the first one. Now in hexa-aqua iron 2 plus, iron 2, this one complex, because the ligand is now water, this is a weak field ligand, the difference, energy difference, and splitting is small between T2G and EG. So when you fill it up, 6 electrons here, 1, 2, 3. Before pairing the first one, the energy difference is small enough. Now it's better. In energy-wise, it's better to fill up singly the top one, 4 and 5, and finally the sixth one should be pairing like this way, this one. But in the case of weak field ligands, strong field ligands like Cn negative cyanide ion, the energy difference is not large. Now let's fill it up, 6 electrons in this situation. So hexacyanoferrate ion, we have this one first, second, and third. Now if this energy gap is small, it's better to fill it up the fourth and fifth, but this energy difference is so high. Now it's better to pair them up before filling up this high electron unstable one. It's better to pairing them. So then fourth one is now coming here and pair them up, pair. All the sixth one is now leading up to all paired electrons. So because this ligand is different, the energy, the electron configuration is now different. So here in now hexa-aqua ion 2 is now we have only one paired electron, 4 unpaired electrons. But here in this case, hexacyanoferrate ion, we have all paired electrons, no unpaired electrons resulting. Now let's see this one, hexacyanoferrate ion, more in detail. With strong field ligands such as cyanide ion, the energy splitting is now larger than the pairing energy. So it's better to pair the electrons because the energy gap is so high. So electrons pair in the low energy T2G orbitals before occupying the EG orbitals. So we pair them up 1, 2, 3, 4, 5, 6. So we have 6 electrons all pairing. We have 3 pair of electrons in T2G subshell, T2G energy level. But in hexa-aqua ion 2, this one complex, the storage is different. Weak field ligands, water is a weak field ligand, so the ligand splitting, energy splitting is less than the pairing energy. So it's better to singly place the electrons upspin, all the upspin up to the EG orbitals. The sixth one is now pair them up with the first electrons in the T2G subshell. So electrons occupy all d orbitals singly first before any pairing occurs, because its energy splitting is not small. Now we can do example high and low spin complexes. Predict the number of unpaired electrons in each of the complex compounds. Here now, potassium hexaiodo chromate ion right there. So this one should be 3 negative charge. You can figure out the number of d electrons, and you can go next time. Iodide ion, this one is now weak field ion, weak field ligands here. You can figure it out. Similarly, you can do here and here. Take time to predict the number of unpaired electrons. Now next one, let's move on to figure out the electron configuration and geometry and tetrahedral geometry. Orientation of the tetrahedral ligands are shown on the right hand side figure here. So at the center we have metal cation with the d orbitals, and then the ligands are approaching from the corner of this cubic structure. So we have this cubic structure has 8 corners, and on the diagonal side of each corner, we have 4 ligands are located. Tetrahedral has 4 ligands. These 4 ligands approach. Then this one is now DXG orbital. DXG orbital is now in between Z orbital. Orbital is along in between 2 axes, and they have relatively close in their distance, so the repulsion is high. So this one forming unstable electrons. So XY, YG, and ZX, these 3 orbitals have relatively high energy level. So T2G is high, but the orbitals of dx square and y square, they are on the axis of x-axis and y-axis, and then the distance between these ligands and this orbital is relatively further away, so the energy is more stabilized, less repulsion and energy stabilized. So in tetrahedral geometry, EG is lower than T2G in their energy level. So E is now lower than energy level T2 level. So energy difference split is now relatively small because they are not overlapping on their linear way. They are a little bit tilted on their axis. So small energy difference between this one E and T2 level. Usually the magnitude of this difference is now 4 over 9 times of energy splitting in octahedral geometry. So now we can apply this crystal field theory to figure out magnetic moments, magnetic properties. Now let's remind ourselves there are 2 terminologies, which is paramagnetic and diamagnetic. Paramagnetic material is now responding to the external magnetic field. They are attractive to the external magnetic field. How can you recognize it? Due to the presence of unpaired electron. If the structure has at least 1 unpaired electron, then it becomes paramagnetic. When the paramagnetic material has more and more unpaired electrons, the paramagnetism now increases. Now, when you draw the electron diagram and electron configuration, they are all paired up. There are no 0 unpaired electron, then it is leading up to diamagnetic property, which is now non-responsive to the external magnetic field, or actually a little bit of repelling upon this external magnetic field. This one is called diamagnetic. So now let's look at these 2 cases. Hexa-aqua ion, this structure, we draw this one before. We have 4 unpaired electrons right there. So this one is now strongly paramagnetic. This one is now responsive to the external magnetic field. This one is attracted to the external magnetic field. But this one, hexacyanoferrate ion, has all paired electrons. So this one is diamagnetic, unresponsive to the external magnetic field, or slightly repelling to the external magnetic field.